finishing up 3.1, so we'll be reviewing everything we learned yesterday, period, amplitude, things like that, and then adding to it, of course. Again, tomorrow we'll do the first day of 3.2, which is when we kind of start working on the unit circle. And then a day to get caught up, especially today. You might not finish today's homework, which is okay. Remember, when you have a work day coming up, you shouldn't feel stressed about that stuff. And then we'll continue on next Monday. All right, so let's take a look at the beginning of this period. It's telling us this is a periodic function. So remember, periodic function repeats its pattern of y values over and over and over. And just so, oh, my battery's not low. 1 second, or it's going to stop. It's going to die. I guess I didn't have that plugged in all the way. Okay. Ooh, good thing I cut that. And so, guys, just so we're clear, all right, guys, no more talking, please. Your periodic function repeats forever and ever and ever in both directions forever and ever. So what we're looking at is not just the whole graph. It goes on forever and ever, okay? So first thing is, what is the period of this function? What's the period? So find your pattern that repeats. It doesn't matter where you start, as we talked about yesterday. You could start here, you could start here. It doesn't matter as long as you can see that you get back to where you started. So I might see like an upside down V, almost look like a capital A. You might see a V. They're both right, okay? It doesn't matter. They both start and end at the same place, and they use the same amount of the x-axis. So from -5 to -1, or you could look at it as from 2 to 6. Either way, what is our period? 4. And for the sake of this problem, we're going to call it lowercase k, okay? And then if we were going to continue the behavior, continue this graph, we just want all of our mins and maxes to be exactly the 4 apart in this picture. So if I just do 1, 2, 3, 4, 1, 2, 3, 4, I could just keep making these like these or whatever you want to call them. 1, 2, 3, 4, look at this here. And of course it would go off the graph at some point, but it keeps going. Okay, so we should be able to like continue it if we needed to. So that's part B. Now this next one is kind of new. We've got some new notation in here. What this is this little formula right here is a way of proving, showing, finding. You find whatever word you want to plug in there. Proving, showing, finding. If I know one of my minimums or one of my maximums, how can I find all the other ones? Okay? So in this case, and I'll explain the formula and what all this says as I go through it, but what it's saying is for a minimum. So any minimum, what we're going to start with is pick any of the minimum values, okay? So any one that we want. I'm just going to pick this first one we came to, but I'll repeat this many times. If this was a homework or a test, you could use this point or this point or this point or this point or this point. Any one of those 5s would be fine. But for the sake of us all doing it together, let's just use this one. Okay, so what we're going to do is plug in to this formula. X is this x. Okay, so for the sake of this problem, x is going to be -5. N, 1, 2, 3, and so on, is how many times we move to the next one. So right now, if we're calling this our the point that we're working with, -5, -2, would be considered n is 0. It's our starting point. N is 1 would be this one, 2, 3, 4. And then you could go backwards. You could go -1, -2, -3, and so on. That's n is like number of times you move. And then k, for the sake of this problem, is 4. So I'm just going to plug those numbers in. Let's find 1. Okay, let me just do it first, then I'll explain what it means. So when I simplify that, -5 plus 4, I get -1. So what that means is I should have a minimum at this point. Do I? Do I? Yeah. -1, -2. Where did I get the -2 from? Here. Because on a minimum, they all have the same y value. Okay? So, stay with me. Let's do another one. Let's predict, prove, show that the next one would be 2. So we're skipping that one and going to this one, right? I'm checking, verifying that that is the minimum, the next minimum. So that would be -5 plus 8, which is positive 3. Sorry, positive 3. So what that means is f of 3 is -2. So when x is 3, y is -2. Is that the case? Yes. So how could this be helpful? Well, what if you just, without drawing the graph, you wanted the point backwards or 5 points back? You could put in a -5 in here for your end value. If you wanted the 10th minimum from this one, you could, you can just kind of see what that would be used for. So we use this for minimums or maximums, and the notation just looks kind of funny, but if you just know what the variables mean, that's really all. So it's just showing, yep, we just showed for 1, 2, and I could keep going if I wanted to, but we don't need to, okay? This next one is number 1 in your homework, so I'm not going to do it. It's pretty simple. What you're doing is graphing, sketching a graph that represents this. So months is your time, amount, or average high temperatures would be here. So 1 through 12 would match up with January's 1 and so on. And you would sketch that graph, describe, find the period, and find the amplitude. So using the same information we used yesterday, okay, which I'll review in another problem here next. Okay, so I'm not going to do that one. But this one is really, really important. So let me read. We're on example 9, and I know you're missing this part F, but you need to add it. Okay, part F. So let me read while you're writing that. Periodic functions take on characteristics of other functions, such as intervals of increase and decrease, concavities, and various rates of change. However, with periodic functions, all characteristics found in one period of the function will be in every period of the function. So if you think back to Unit 1, Part 1, our very first test, we talked about concavity, we talked about increasing and decreasing, mins, maxes, absolute, and local. We talked about, what else? Rates of change between 2 points, all that stuff. Same thing, just different graph. The difference is, like if we did it with a line or a parabola, we just answered about that one graph, right? It had one concavity or whatever. But with periodic functions, it repeats over and over and over again. So we're going to learn some new notation to help us be able to state that correctly. Okay, but let's start out by looking at this graph. It tells us it's periodic. Let's find the period and the amplitude, which is something we learned yesterday. So start wherever you want, as long as you complete one full pattern, end up where you started. So like, for example, if I start at 0, I would end up at 8, right? That would be one full period. So my period is 8, right? The pattern repeats every 8 pieces of the x-axis. Amplitude, we have a formula for it, which I'll review in our last example here in a bit. But a nice thing to notice is that whenever the amplitude, the max and the min are the same value of 3, so up 3, down -3, that is your amplitude. Okay, you could do half of the max minus the min, but you would get 6. Half of 6 is 3. So you don't really need to use the formula. Save yourself a little work where you can. And we just talked about what the max is +3 the whole way down, and the min is -3 the whole way down. Okay. So max and min, how high or low, those are your y values. Now, let's talk about concavity. Concavity, I know you guys can look at that and tell me where concave up and concave down are, but let's remind ourselves of a couple things. So I'm going to use a highlighter to kind of help us understand this. Concave up. So I'm going to highlight in pink all the places where we're concave up. Just on this graph. We know it repeats. But in our viewing area, those are the parts of the graph that are concave up. So back when we just learned about parabolas and talking about concavity, let's pretend that it's just a parabola right here. You would have said this graph, this parabola, is concave on the interval from -4 to 0. In parentheses, just naming the x-axis, you would have said -4 to 0. Okay? But not really. It's not more complicated. It's just something new we have to kind of, new way of noting it. Why would I just say -4 and 0? I see another place where it's happening, from 4 to 8. And then I know, wait a second, it's going to happen that way and that way over and over and over again. So pick one set. You can use this set or this set for the sake of us doing the same thing. Let's talk about this one right here. So watch how I'm going to write it. With concavity, we always use parentheses. Interval means the x-axis. So we don't care about what is happening on the y-axis for concavity. So watch how I'm going to write this. From -4 plus or minus 8n, comma, 0 plus or minus 8n. So think about what that is saying. We just learned what n means on the other page. N is how many times we move to the right or to the left, okay? 8 is our period, because look, if I'm going to use -4 to 0, which I did, this right here is showing concave up, where does it happen again? It happens exactly 8 away from each of these points. So look at my pen. This point right here matches up with this point right here, right? That's where the concavity begins again. How many places away is that? 8. Same thing here. At 0, I'm going to match up with 8, which of course from 0 to 8 is 8 places away. So that's adding 8 one time. You could add 8 a second time and get the next one. Add 8 a third time. What about the minus? Well, that's just going in reverse, okay? So this is a way of saying, here's one of them, and you can find all the rest by counting all these places, 8 to the right or 8 to the left, as many n times as you'd like to, okay? There's another notation I'm going to show you after I do concave down. So let's do concave down. And again, in your homework, on a test, quiz, whatever, you did not have to use -4 to 0. You could have changed -4 and 0 to 4 and 8. Totally the same thing, okay? Same with concave down. There's 2 of them that I can see their complete picture here. I could use from -8 to -4 or 0 to 4. Either one is the same thing. It means the same thing, okay? William, you paying attention? So again, concavity is parentheses only. So I'm going to just use this one. -8 plus or minus 8n to -4 plus or minus 8n. And for the same reason as we just saw with concave up, that's why we have the 8n. That repeats over and over and over. Now, I'm going to add a new symbol. So you might want to just find a place to write it. I'm going to put it up here. Here's a new symbol. Series of symbols. N. Do I have any Greek people in here? Anybody that knows Greek? No? I keep saying I'm going to look it up and I keep forgetting. So, yeah, it is. So, this is like a double line right here in the middle, a line through it. I call it Z, and I write it really fast, and it looks like that, which is totally fine. So if I was just going to say this to you, it'd be NEZ. NEZ. Okay, let me tell you what it means. N is a variable. Okay, so that could change. We could be talking about X, we could be talking about R, Z, whatever. We're talking about N in these problems. That's why I have an N there. This E, which I believe is, I'm going to look it up, epsilon, Greek letter epsilon. By the way, trigonometry was developed. We give the Greeks the credit for that. They are the ones that really developed that part of mathematics. So there's a lot of Greek letters in what we do in trig. Yes. Say it again. Is it? Okay, thank you. I should know that. My daughter was in a sorority called Zeta, and she had Z's on everything. Anyway, E is belongs to, that symbol means belongs to. And that zeta, thank you, is, how did I write it? Set of all integers. Now I'll give you a second to write it, and then I'll explain what it means. But you are going to put that after both of these. So n belongs to the set of all integers. Integers, whole numbers. Positives and negatives, 5, -5, not 0.5, 0.2, 1/2. Okay? Because, so I like to think of any z as like the positive or negative to positive infinity for trig. So when we talk about all the numbers from left to right, we say it all the time, right? From negative infinity to infinity. We're including decimals, fractions, whole numbers, everything, right? Positives, negatives. Integers are positive and negatives, but no decimals, okay, or fractions. So, in other words, we are stating by putting this that you're not going to put a 0.5 in for n. It has to be a whole number. You have to go a full 8 in each direction, okay? So it's just trig for negative infinity to infinity, all right? Now, notice, concavity, we use parentheses only, never use brackets, and we only use the x-axis. -4 and 0, -8, -4 are all x values. Concavity, even though it's about how you're opening up and down, is only named, whenever you see the word interval, it's x-axis. Now, point of inflection, points are x's and y's. So we use parentheses again, but we're actually calling it an ordered pair. Well, points of inflection, review, is where you change, where your graph changes from concave up to concave down, or vice versa, concave down to concave up. So all of these x's are points of inflection. And it goes on forever, NEZ, all right? So how do we list that? Well, you pick one. Pick any one you want. Just like you could pick with these, pick one. 0, 0, 4, 0. I don't know. I'm going to be boring and pick 4, 0. I don't know if that's boring. But why? Well, you guys tell me, what am I going to write after the plus or minus? Look at the graph. Look at the graph. What am I going to put? 4n. Wait, she said to use the period. I did. That's how far apart the concavities were, right? Our concavities were 8 apart. You have to be able to look at the graph and analyze it. This isn't memorizing. It's not going to be the same thing every problem. So if I look at my graph and I see there's a point of inflection, and there's one, and there's one, how far apart are they? They're 4 apart. They're not 8 apart, okay? And we can go to the right however many times we want, and to the left however many times we want for the positive and negative. Okay, and then the NEZ. All right, so lots of this stuff is such great information, such great things to be reviewing, because it's reviewing stuff from the beginning of the year. And I'm not going to do example 10. I'm going to do one other example with you in a second, but I want to tell you a few things about example 10. More of that stuff, characteristics of graph that we have to know. We just talked about period and amplitude, max and min, okay? Here's 2 we didn't cover, intervals of increase and decrease. You see the word interval, you go, that's x-axis, but here you use brackets. So these are brackets. This is memorization. And if you remember, we talked about it a lot before the first test. Don't forget, you don't want to lose points because you use brackets for concavity and all that stuff. So these are all big items that we're going to be reviewing before the AP exam, of course. But brackets and x-axis only, because it says the word interval. And that's always been the case. So, but look at these graphs. Look at this graph. We have, by the way, for max and min, we have 2 different maxes, okay? So you would list both of them. The only time we care about the biggest one is when we're trying to find amplitude, the highest point, the lowest point, the absolute max, or global max. But this is a maximum too. So you'll have 2 maxes, 1 min. Having said that, you'll also have just one interval of let me say that again. Actually, you'll have two. Let's talk about increase. Where's increase? That would be, yeah, here or here. There's two of them. So that's from -2 to -1. And then this one would be from 2 to 3. Just the x-axis. It's using a very small part of the x-axis. And then there's 2 for decrease as well. And then last thing I want to talk about, and I'll have the key up and I'll be walking around and helping you. I just don't want to spend too much time on the notes because a lot of it's repeating. AROC. What's the formula for AROC? Known as what? Slope. So remember, these are intervals. That means these are the x values. So if I wanted you to find the slope between 2 and 3, that means x values 2 and 3. So you would go up to the graph and get your y values and then find the slope. Okay? But I showed all this work. I just wanted to kind of remind you of some things. Right? So a lot going on with these types of problems. Really big ticket items, knowing how to evaluate graphs, pull out the information. Okay? The last example we're going to do is example 12. I told you guys yesterday that you would be learning more about pedals on a bike and Ferris wheels than you ever thought you needed to know. And here's our first Ferris wheel problem. I'm telling you, you're going to see Ferris wheel problems all the time. The Orlando Eye. Remember people got stuck on that like a year ago or so? Like for a long time. Like a long time. I would have a heart attack. I am so claustrophobic, I would lose my mind. Okay, a Ferris wheel at the Orlando Eye attraction is 120 meters in diameter. I'm sure that's important. The height in meters of a compartment H is a function of time t in minutes. It takes about 30 minutes to make one complete revolution. Okay, so let the height of the car where you enter the ride represent the height at time 0. Okay, so my artistic skills are going to come through today. Don't be jealous. Okay, here's a Ferris wheel. Okay, and we're going to say height at time 0. Let's call it just being on the ground. Okay, I'll talk about how that will change. So if this is the ground, at 0 seconds before we even start, we're at 0 feet off the ground. I'll just say it now. Sometimes the Ferris wheel questions will say there's a 4-foot like steps that you have to go up to get in. So that would change this to at 0 seconds we're 4 feet off the ground or something like that. Okay. And we make a full revolution. Now, by the way, it doesn't matter if you want your personal Ferris wheel to go around clockwise or counterclockwise. It's not going to change anything in the problem, and you'll see that as we go. For some reason, I keep doing it clockwise, although I haven't been on a Ferris wheel in like decades, so I don't even know. Do they go clockwise or counterclockwise? It does? So you go backwards over the back of it? You don't go forward? You're not laughing at me, you're laughing at me. No. Okay, all right, it doesn't matter. Okay, and I'll point out why. So diameter, let's go back to that. That's how far across or how high it is, right? So our Ferris wheel from the ground to the highest point would be 120 meters. So that's our height at some amount of time. So I know that that would be 120 when I'm at the highest part, okay? So if it takes 30 minutes to go around, that means I'll be back down on the ground 30 minutes later at a height of 0, right? So that those 2 points are shared. Yeah, remember how they have to stop and let people on and off? So annoying. Let me go. I want it over with. How much time till we get to the top? 15, right? Halfway there, 15 minutes. So at what time does the Ferris wheel reach its maximum? 15 minutes, let's fill that in. Let's find the amplitude. Back to part A. Find the amplitude. We have a formula for that. Half of the max, which is 120, minus the min, which is 0. So half of 120 is 60. So our amplitude is 60. And we're going to sketch a graph of this. So right now we basically have 3 points. We have 0, 0, we have 30, 0, right, where we start and where we end. And we know where we are halfway, which is 15 minutes will be at 120 feet. Let's get two more nice and easy points. Let's figure out half of halfway, or quarters, okay? So whether you're going this way or you're going this way, it doesn't make a difference, and you'll see why. I'm going clockwise, so I'm going to call this one. How many minutes would be half of 15? 7.5. And how high am I halfway between 0 and 120? Right. So keep going. Let's get this point here. What's the height right here? Still 60, right? I think it's still 60, but it's a different amount of time. It's 7.5, 15. We would need to add 7.5 to 15 on my calculator, 22.5. And then, of course, 7.5 minutes later, we get down here, right? So basically, dividing 30 by 4 is 7.5. So 7.5 plus 7.5 plus 7.5 plus 7.5. And so it doesn't matter if you called this 7.5 and this 22.5. In other words, it doesn't matter which way your Ferris wheel is going, clockwise or counterclockwise, because the heights are the same, okay? So at 7.5, I have 60, around there, and at 22.5, I'm at 60. So either way, whether you went clockwise or clockwise, you have points right there, okay? And then that's a good graph. It's pretty good. You should have seen the one I did last period. I didn't even hit 1 point. Okay? But there's a sketch of that graph. Obviously, we only have a few good points, but we can connect them and make it curvy, and that's good enough. Okay? So we'll be seeing Ferris wheels a lot. A lot. All right. Question before I give you the homework. Okay, so 1, 4, 5, and 6, and you always do all parts unless I omit one. So in number 5, omit part E. Don't do part E, but do all the other parts of all the other ones. Work together, ask me for help. Okay. I'll have it written down.